Hello and welcome. In this lecture, I'd like to talk about debugging. This is a very important concept that you need to understand. Specifically, you need to understand some of the tools and some of the methods that you can employ to find and fix bugs. So debugging is the process of finding and fixing errors in a program, usually logic errors. And I'm going to tell you the difference between logic and syntax errors. But it can also include compiler syntax errors. It's the entire process. For syntax errors, debugging is understanding what the compiler is telling you. You always want to focus on fixing the first problem detected. I want to go through some of the common compiler errors and warnings that you may get, but one of the things you always want to know about the compiler is that the compiler may give you a number of errors. You always want to focus on the first error because that first error may result in other errors, so it can be very misleading. If you see 5 errors in a program that the compiler is telling you, you might only have one error, and that first error might be causing the other errors. So it's important to always look at that first top error and fix that one first. Debugging and the process of finding and fixing bugs can be very complex, from finding simple errors to collecting large amounts of data for analysis. It all depends. Sometimes you don't have any information provided with you except logging. And in that case, you have to analyze things. Sometimes you'll have bugs that aren't repeatable. You can't reproduce it because it happens in such a rare occasion. That's usually when you have to analyze logs or some variation of that. The ability to debug by a programmer is an essential skill. It's really a problem-solving skill that can save you tremendous amounts of time and money. So it's an important skill to learn. It's an important skill to develop. It takes practice. It's not just going to come to you. There are certain techniques that you can apply and methods that you can apply to make you better at debugging. I know quite a few number of developers that are really good at writing software, writing code. They understand the language very well, but their debugging skills are very poor. They may get a bug and their first inclination to solving that bug is really kind of off track. And again, this comes with practice. You'll get better and better at debugging and understanding how to find and fix problems. But it is something you have to learn as well. The maintenance phase is the most expensive phase of the software lifecycle. The maintenance phase is after you release your product and you now have to maintain it. Maintain it means fixing any new bugs that come in and also adding new features. So for example, when Windows releases a new operating system such as Windows 10, they're not done producing that software. It's going to be out in the field for probably 10 years. And it's still Microsoft's responsibility when any new bugs come in or they find new bugs for that software to fix it. And that's why they push auto updates and they do things like that. And then they'll also notice that the operating system will come out with new features as the market changes and as technology changes. So maintenance is very important. And as a result, finding and fixing your bugs is very important. Understand though that bugs are unavoidable. All software have bugs. Nobody can write perfect code. And it's not even necessarily about writing perfect code. It's just things change over time, so that may result in bugs as well. You have to understand that just because software has bugs does not mean it's poorly written code. It's kind of unavoidable. So it's okay to have bugs, and when you find and fix them, it's even greater because you actually feel like you're accomplishing something. Common problems, and we're going to talk more about specific problems related to C, but common problems when you're trying to debug are logic errors. Logic errors have to do with with the opposite of kind of syntax errors. Your code actually compiles, it works, but it doesn't do what it's intended to do. So there's some kind of logic or intended functionality that's incorrect. Maybe you have an if statement and you're jumping into that if statement on the wrong condition. Maybe you have a loop and the loop is not executing the right number of times, or you're not sorting correctly. Functionality is broken, but the compiler says, hey, everything looks good. Syntax errors are directly related to the compiler. These are things not following the rules of the language. You don't have a semicolon at the end of a statement. You don't have a ending right parentheses with a left parentheses. You're missing a bracket. You're not using the right keyword. Things like that. Syntax errors are usually caught by the compiler. Logic errors are going to be caught by the programmer during the testing phase. Memory corruption is also a common problem, especially in C. If you're not freeing your memory after allocating it correctly, you can have things like dangling references, and you can also have memory issues related to memory that's not being used. You can have memory leaks. Performance and scalability. This could be a problem where your functionality is intended as it is, and your code syntactically is correct, but it's not very efficient, or you don't have the hardware to support it. So if you're running a server and you don't have enough hardware to support all the requests, it's going to run really, really slow. Or if you wrote your program to work with 10 users, but when it gets a lot of users, maybe it's not as fast because the database gets bogged down, or whatever the case may be. Code works, but it's not designed correctly to handle many amounts of users, or whatever the case may be. Lack of cohesion. This can be a problem in your code that reduces quality related to your code is doing too much, or a function is doing too much. It's not a single focus. Or even an application has too much functionality, has features that are never used. Right? And so this would probably require a redesign. Tight coupling. This also has to do with quality of code. This is where you have a lot of dependencies. Coupling is different than cohesion. Cohesion is your single focus. Coupling is where you have dependencies between maybe functions or between objects. We talked about coupling. We talked about global variables. If a global variable is being used in a lot of different functions, it can cause dependencies between those functions. So what you want to strive for when you write code and you're writing high quality code is you want to have very high cohesion and very low coupling. The debugging process, the first thing you have to do before you can find and fix any error is you have to understand the problem. This is relatable to don't just dive in and start looking at the code. Sit down with the tester, understand the requirements, understanding what's going on. Because if you don't understand what's going on, you're not even going to be able to, you shouldn't even attempt to try to solve it. Once you understand the bug, try to reproduce it. Because reproducing the bug can help you gather more information. It's not always possible to reproduce bugs because they may occur in really rare circumstances. So for example, bugs that have are race conditions or even memory corruption may only happen in very specific use cases. And they may be intermittent problems. And if that's the case and you can't reproduce it, it's going to become harder and harder to debug. If you're able to reproduce it, you can usually gather enough information to fix it. Most problems are fixable. Also, you can have problems with not being able to reproduce a problem if you're a multi-threaded environment, parallel processes, or threading problems. Those are also very hard to debug. But definitely try to reproduce it once you've figured out what the problem actually is, in terms of you're able to understand the. Once you're able to reproduce it, or if you're not, then you want to try to apply some kind of divide and conquer. You want to try to isolate the bug, simplify the problem. Because being able to reduce is going to give you information back, but it might not necessarily tell you what part of the code the bug is in. So what you can do to try to simplify the problem is remove parts of the original test case so that you're not testing too much. You can isolate the problem even smaller by saying, oh, it only happens in this specific situation. You can also comment out code. We talked about functions just having stubs and not having any implementation. Sometimes that's employed in testing so that it can limit the problem set. Also, if you comment out code, you're going to have less code where the bug can actually happen. So as you're commenting out code or backing out changes, the bug may go away. And if the bug goes away, that tells you that the code that you commented out may have been causing it. What you essentially want to do, though, is turn a large program into a lot of small programs, either via testing or commenting out. Another common technique is to have unit tests surround your code. If a unit test fails, that can tell you exactly where the logic or the problem might be in your code. Once you isolate the bug, you can, and that will help you find the origin of the problem in the code, the specific code that's causing the problem. Sometimes this will employ using debugging tools, such as a debugger. We're going to talk about a debugger in specifics, but usually, depending on what IDE, integrated development, you use, there's debuggers that come with the IDE. There's also debuggers that can land standalone. The big important debugger that we're going to use for C programming is called GDB. It's the GNU debugger. It's also integrated very nicely into code blocks. So it's a nice tool that's actually a graphical tool in code blocks where you can stop the execution of your program and add in breakpoints. And then as you stop the execution, you can go line by line in your code and look at the value of variables. so you can see exactly what's going on in your code while it's running. It's an invaluable tool. It's so useful. We're going to run through the debugger and visual blocks. I'll show you how to add breakpoints. I'll show you how to set up a watch so you can look at variables as they change, and also then step through the code. After you've identified the origin of the problem, you then have to fix it. This takes a lot of experience and practice. Just because you found the origin of the problem, you still might not be able to fix it just based on your experience. This sometimes includes redesign or refactoring of other code that especially with scalability problems or performance problems, you may have to redesign to allow your software to be more scalable. So it's not always easy just finding the problem and then fixing it. The problems sometimes, especially even harder problems like threading or parallel processing, those are even more difficult to fix. But as you write more and more code, this is going to become easier to do. And then lastly, you got to test like crazy. Always test. Test many different boundaries, good cases, bad cases, in-between cases, to verify that you have indeed fixed the problem. Some of the techniques and tools that are available. One common and very used tool is to use print statements. You can use print statements to basically trace your code. So in C, you can use the printf statement, and you can put it at multiple lines in your code to signify where you are. This is also very useful when your program crashes. It can help identify where it crashed. As you're adding these print statements, tracing through your code, you can add output in the print statements to see the value of variables, because the value of variables may be affecting state and may be causing logic issues. So just adding print statements is very useful. It can show the flow of execution, and it can help isolate the error. Debuggers, as I mentioned, one in the code blocks, GDB, those can monitor the execution of the program. You can stop it. You can run line by line, restart it, set breakpoints, watch variables in memory. Very helpful when trying to diagnose where a problem resides. Log files. Log files are also very useful, especially for bugs that cannot be recreated. You can analyze them at a later date to see exactly what was going on when the bug happened. So this means that you have to provide good logging statements in your code itself in order for this to be useful. So you may create your own log file and then write to that log as the program is running, so that if you do have an error, you can send those logs out to developers. We employ this quite a bit at Xerox, because when we encounter issues, we can't always reproduce them, or they may be encountered in the field. We need to be able to access those logs to see what was happening when that bug happened. Monitoring software. There's software that can monitor and have runtime analysis of memory usage, network traffic, thread and object information. This can tell you if maybe you're allocating too much memory and not deleting it if you have a tool for memory usage. Network traffic, that can tell you whether or not you're sending too many packets out or whether or not your software is scalable. If you have an increase in network traffic and you see that your response time is degrading. You can also monitor threads and objects information for parallel processing to see what's going on in certain threads and what's going on in another thread. That will help you diagnose any thread kind of problems. Some other common debugging tools that you can employ to find and fix your errors. You can use exception handling. Many programming languages have exception handling. Unfortunately, C does not. An exception handler will actually prevent crashes and do a lot of things at runtime. It doesn't apply to C, but it's still a good thing to understand. Try catch blocks, things like that. Static analyzers. There are many static analyzers available for C. Static analyzers analyze the source code without the actual executable running. The program doesn't need to run it. It goes line by line and looks at the source code, and as it's parsing the source code, it looks for any known problems. So it can check semantics. It can make sure that you don't have any uninitialized variables. If you're allocating new memory, that you delete it. If you have any dead code where code's not actually being executed, you can delete that code. It also analyzes things like race conditions and deadlocks. We employ a couple static analyzers. Where I work, we have one called Coverity, which is pretty popular, and there's a code sonar tool that we use as well. And we'll run this on our entire baseline, our entire source set, and whenever we introduce new files and new code, that tool will be run on that code and will be able to identify immediate issues with the code as far as uninitialized variables, memory leaks, and so forth. It does not analyze syntax. That is what the compiler is for. There's also a number of test suites that run a set of comprehensive system end-to-end tests that you can run on your software. Testing is always important, but if you can automate it somehow to run certain tests every time you do a new build, for example, that can be very helpful. And this can actually prevent errors, but it also helps diagnose errors as well. Debugging the program after it has crashed, we're going to talk about something called the call stack. This is a very useful mechanism to see, especially in a language like C, where you have a crash and the only information that you get is something like segmentation fault. When you have that crash, what happens a lot of time, depending on how it crashed, a core file will get generated. And you can analyze the core file to look at the call stack to see exactly where that program died. It will tell you the line of code where the program died. And so we're going to learn about the call stack. And as far as analyzing core files, that's more of an advanced technique. But in C, a core file can be generated and you can analyze it. That's a little more advanced technique. But that's another way you can do debugging on your software. What about preventing errors? We know that debugging is finding and fixing errors, but if you can prevent errors, that's even better. One of the ways that you can prevent errors is you can write high quality code. This is really not a focus on many software engineers. A lot of software engineers write the code, and as long as it works, that's all they're concerned about. Or as long as the output is correct, then they consider themselves done. But there is such a thing as poor quality code. And you don't want to write that. I've demonstrated some of this during the lectures, but things like using meaningful variable names, very important. Or if you write inefficient code where you're using loops maybe more than you need to, or using an if statement where you don't need to do that. All of these types of things constitute poor quality code. If you have a function that's doing 100 other things and it's not cohesive, if you have 5,000 lines in a function, if your code is not organized in a module fashion, or if you have many dependencies between functions. Again, all of this is poor quality code, and you want to strive not to do this. You want to employ techniques where your program is organized, it's easy to maintain, it's highly cohesive, it has low coupling, and you use meaningful variable names. Very, very important. Again, it's very important also because the maintenance phase is so expensive. If you write poor quality code, it becomes much harder to maintain. It's harder to isolate errors, and it's harder to add new features. So employ good, high quality techniques when writing your code. Unit tests. Unit tests help prevent errors tremendously. Unit tests are executed usually automatically when you compile. Unit tests can help avoid regression. That's one of the most important factors. Regression is when you write new code and you introduce a bug on something that was previously working. You broke old code. You don't want to do that. If some software is working and then something new that you did broke it, you want to immediately be notified. And unit tests can help do that because unit tests will run on that old code and will say, hey, this was working, now it's failing. It also can find errors in new code before it's delivered because, again, they run after you build, and it will immediately tell you if something's wrong. There's a concept of test-driven development, which is getting really, really popular. This is where you write your tests first, and then you develop your code after. And the goal here is when you write your first test, your test is failing. And then you write the code to get it to pass. There's a lot of advantages to TDD, and it's kind of a reverse way of thinking. Normally people, when they write code, they write the code first and then they write the test after. But with TDD, it actually gives you a different way of thinking so that you're working in really small chunks and you tend to write very cohesive code, and the code doesn't have a lot of dependencies. Because guess what? If you're able to test code, it means that the code doesn't have as many dependencies. If your unit test is really, really large and you're mocking out all these different things, it's usually a big indicator that your code is very, very dependent on other things. So by employing TDD, it forces you to write very loosely coupled code that doesn't have dependencies, and it forces you to have your functions be very cohesive. There are a lot of advantages of TDD. You also want to provide good documentation, and you want to do proper planning. Don't just dive into code and start implementing. Write down your design on paper, utilize pseudocode. All right, plan your code. If you plan your code, you understand the requirements, and you have a good, thoughtful design, you can prevent many, many errors. And I've mentioned this throughout the course, but it's very, very important to have a divide and conquer type approach, work in small steps, and constantly test after each step. Do not write 1,000 lines of code and then say, okay, compile and test. That is not a good approach. Avoid too many changes at once. When making changes, apply them incrementally. Add one change, then test thoroughly before starting the next step. This can help reduce all sorts of bugs, and it also limits your problem set. So if you do have a bug, you immediately know where it is in the code because you just compiled and you just added that line or number of lines. Again, I cannot emphasize the importance of debugging, writing high-quality code, and preventing errors. These problem-solving techniques will save you a ton of time and make you much better programmer, top-tier programmer. So in the next few lectures, I want to talk about some of the common errors that we see in C programming language. Also, I want to talk a little about the call stack. I want to go through the debugger that CodeBlocks provides and introduce you to the menu options and how you can stop and run watches and so forth. And I also want to help identify some common compiler errors that you see, how to interpret the compiler warnings and errors. What does it mean if the compiler says this? What does it mean if the compiler gives you this warning? Thank you.